Good afternoon. So today we begin the last topic of the class, the polar coordinates, another very useful way to represent points in the plane, and I hope that we will illustrate by the end of the class why this is so useful in many situations. You'll make much more use of it in later classes like Calculus 3 or partial differential equations as an example. So it's an important topic, especially if you continue with calculus-related topics. Now, things are very straightforward, in fact. The difficulty in the beginning is that you need to, if you see this for the first time, you need to be patient in the beginning until you learn how these coordinates are defined. Because since you didn't use them before, they don't come that natural as the Cartesian coordinates. But they will become natural once you have enough practice, like with all things math-related. So to give you an example, you know, as we all know, right, if you look at the Cartesian coordinate system, and if I want, for example, to plot a point of coordinates -3 and 2, you know already that x equals -3 looks somewhere here to the left of the origin and 2 above the origin on the y-axis. But this is so easy and second nature to you because you already know the convention that on the x-axis, negative numbers are on the left to the origin, and on the y-axis, positive, numbers are above the origin and negatives below the origin. Because in the case of polar coordinates, the two numbers that identify the point, you're still gonna need two numbers to identify each point, two coordinates. Those two numbers will have a different meaning, in the different geometric meaning, and also in that case, you have to make some convention of what we mean by a positive or negative. And actually for the angle, you probably know that already from trigonometry, but for the other number, it's probably new in terms of its meaning. So without further ado, let's go over how we construct this coordinate system, and then we'll obviously deal with plenty of examples after that. So we start with a point called origin, just like in the coordinate system. So we're going to have a point O called the origin or the pole, and a semi-axis, which is called the polar axis, which for convenience, because we always have to make the connection with Cartesian coordinates later, for convenience this is identical to the positive, or superimposed to the positive x semi-axis. I mean, it doesn't have to be, there's no meaning in terms of the x-axis. I mean, just the semi-axis will do as long as it's fixed, right? So these are the fixed elements in the coordinate system. An origin, a pole, a point called origin and denoted by O, and a semi-axis which for practical purposes will coincide with the positive semi-axis in the Cartesian coordinates, positive x semi-axis. That's why you draw it horizontally. Okay, so then any point P on the plane, and let's write this in words before I actually sketch. So any point P in the plane will be identified by its distance to the origin, denoted by r, which is greater than 0. So this is r. And the angle theta measured, the angle theta between OP and the polar axis. Or as I mentioned, the positive semi-axis, positive x semi-axis, because it's superimposed to it. Now, this angle, remember, can be measured in different ways, right? So the one that comes to mind immediately will be like this, counterclockwise, right? I mean, if I measure it from the semi-axis, then I go counterclockwise all the way to OP, this will be theta. So therefore, the point P is identified by these two numbers. The first number, r, always represents the distance from the point to the origin, to the pole. And the second number in radians, by the way, is the angle between OP and the positive semi-axis. Now notice already that this representation is not unique, because nothing stops you to go clockwise from the positive semi-axis. So in fact, when you actually sketch a point in polar coordinates, the easiest thing, or the way I find it easier to think about, is to measure the distance to the origin on the positive semi-axis. So measure the distance over here, whatever that distance should be, and then rotate. Imagine that you rotate that semi-axis until you reach the point in question, and that rotation gives you that second coordinate, the angle. But the point I'm trying to make here is that nothing stops you to make the rotation clockwise. If you rotate it with the appropriate angle, you're going to reach the same point. So you could go theta clockwise, or for example, all the way 2 pi minus theta, right? 2 pi minus theta in the sense that you go full circle and then subtract theta and reach the same point P. Now, the fact that there are infinitely many ways to represent the same point, that's not actually a bug. It's more like a feature in polar coordinates, because it will allow you, for instance, to represent curves traversed multiple times. For example, if you want to represent a circle that is traversed twice, all you have to do is to extend the range of theta between 0 to pi with 0, 4 pi, right? You can have, two rotations essentially. So you have a quick way to represent the situation that you may have in applications in which a curve is traversed multiple times. And finally, I forgot to mention in writing here what we mean by negative theta. Again, although you know that from trigonometry probably. So by convention, theta is positive if measured counterclockwise. And theta is negative if measured clockwise. We're going to go over examples immediately on the next page. But there is also, by convention, a meaning attached to a negative r, which I don't actually use it too often because it's not actually strictly necessary in many problems, but you need to know about this convention in case you see it. So, by definition, the point of polar coordinates minus r theta is the point symmetric to the point r theta on the same line. So for example, if I have here the polar axis, and then let's say this is the point of coordinates r theta, by convention the point symmetric to it, so the distance between, so this is r greater than 0, this is the same distance, r. By convention, this point symmetric to r theta is of coordinates minus r theta. So you have a choice of using the same theta, but the negative r. Negative r always represents the opposite, or the symmetric point with respect to the origin from the point with positive r. So again, you have essentially even more choices now to represent the same point, as I'll show you on the next page. So let's stay tuned for a couple of examples. All right, so let's plot a couple of points in polar coordinates. So let's start with the point P of coordinates, let's say 2 and pi over 3. Remember, the first point, the first coordinate is the radius, the distance to the origin. And then the second one is the angle measured with the positive semi-axis. So let's see, I'm gonna sketch the axis of the Cartesian system just to see how the point looks like in relation essentially to the polar coordinates, right? So this is the pole, and then this is the polar axis. And let me make it thicker, right? Because that's the fixed element in this way of representing the point. So I want the radius to be 2 and the angle pi over 3. So again, imagine you measure 2 units. Let's say 2 units is over here where I drew this little vertical line. And then pi over 3 is positive, is measured counterclockwise. So you rotate that line and let's say you reach pi over 3 over here. You measure the angle pi over 3 and then there you go, this is the point. And you can indicate here the angle pi over 3 and here the coordinate 2, I mean the distance from the origin to the point, or you just again write the coordinates 2 pi over 3 in this order near that point, like you normally do for any point of any two coordinates, right? Like you did it in Cartesian coordinates. Again, the thing is the meaning now is different, right? I mean, the first number is the distance to the origin, the second number is the angle measured with the positive semi-axis. So again, the representation is not unique. For example, you could decide to go clockwise. If I go clockwise, I measure the angle in the negative way. So let's see how much I should measure. From the polar axis in the negative direction, it's minus pi, to which I have to add 2 pi over 3. Because that's this angle from negative semi-axis to the point P. Or you could think of full circle, which is 2 pi, from which you subtract pi over 3. But that's going to be negative, right? Because not 2 pi minus pi over 3, sorry. That's like I said, minus pi, which is up to this point, and then continue to subtract 2 pi over 3. So the angle here is going to be 2 pi over 3 from the negative semi-axis to the point itself. So that gives me minus 5 pi over 3. So exactly the same point can be represented as 2 minus 5 pi over 3, if you so desire. What about what if you want to represent the same point, let's say with a negative radius, with a negative r? Well, negative r would mean if you want to represent the point with a negative r, which in other words negative 2, the question is what is the angle in that case? Well, remember the point with negative r should be opposite to the point with positive r. So this point P is going to be opposite to this point. Let's call it Q. And Q, if I want to measure it with positive r, I have to measure this angle. And if you look carefully, with positive 2, that angle is going to be pi plus pi over 3. So it's going to be 2 pi plus pi over 3, which gives me 4 pi over 3. And so therefore P can be viewed as minus 2 4 pi over 3, right? The opposite of the point with positive 2. So if someone asks you to find or to plot a point with a negative 2, with a negative r, you plot the one with positive r, and then you take the symmetric of that point with respect to the origin. We're going to go over other examples like this, but notice already we have essentially 3 possible representations for the same point. One with both positive r and positive theta, one with a negative r and positive theta, and then you can basically have lots of variations of this, because you can always go full circles multiple times and hit the same point, and you could do that clockwise or counterclockwise. So I'm not gonna bother you too much with this because it can be rather tedious, and I'm not gonna ask you to represent a point in 10 different times, but just make sure you understand the convention, especially what we mean by negative coordinate for both r or theta. All right, so with that in mind, let's go over another example before we move on to a different page. So let's say we want to sketch minus 2 3 pi over 4. Let's do another example with a negative 2. So again, like I said before, sketch first 2 3 pi over 4, and then this one will be the symmetric of that one. So 2 3 pi over 4, 3 pi over 4 is going to be, so let's see, this is the positive semi-axis. 3 pi over 4 is in the second quadrant, right? Because it goes all the way up to pi over 2 and then all the way up to here. So this point over here will be 2 3 pi over 4, and minus 2 3 pi over 4 will be exactly the symmetric to this guy. Symmetric with respect to the origin. And before we move on to the different page, why don't you actually pause the video after I write this example and see if you get the hang of it. So sketch these 3 points. All right, so pause the video and sketch them, and then check with me after you did that. All right, so suppose you did that, and let's see how we do this. So this one, the first one, gives me again a positive polar radius. Make sure you pick the right quadrant, by the way. You should know that from trigonometry, right? So 5 pi over 6, it's still less than pi. So it's going to be over here. The reference angle, you know, the reference angle is always the acute angle measured with the x-axis. That'll be pi over 6 actually here, right? And so 5 pi over 6 is all the way up to that point. So this will be to 5 pi over 6. Again, 2 represents the distance from the point to the origin. For part B, I measure 2 pi over 3, but in the negative direction. So look at the dotted line, right? So I measure the angle on the negative way. Minus 2 pi over 3 is less than minus pi, so it's somewhere here. So therefore the point should be over here. Let's say this is 1, and therefore this is 1 minus 2 pi over 3, right? So this angle here is minus 2 pi over 3. And in part C, again, we have a point with a negative r. We're going to do 1 5 pi over 4 first. If you get the hang of it, you can sketch directly minus 1 5 pi over 4, but let's just do it in 2 steps one more time. 5 pi over 4 is going to be in the third quadrant, right? Because it's greater than pi, so it's over here. So that's 1 5 pi over 4. And then minus 1 5 pi over 4 will be the symmetric one over here. Okay, so I hope it's clear. The next item on the agenda today would be a relationship between Cartesian and polar coordinates. So we're going to continue with that. All right, so the relationship between, let's actually write here the relation between polar and Cartesian coordinates. I'm going to illustrate this for a point in the first quadrant, but that works in any quadrant. So suppose the point is of these coordinates, r and theta, and notice that when you look at the x coordinates and the y coordinates of the point, the Cartesian coordinates, you have basically, they form here a right triangle. So this distance, let me write it like that. So this distance is going to be the y coordinate, and this distance, the x coordinate. So to relate them with r and theta, obviously we have to use some trigonometric functions. So notice that the cosine of theta is the adjacent side. Let's see. I think, I'm sorry, I switched that. This is the x coordinate and this is the y coordinate. So cosine of theta is the adjacent side over the hypotenuse, so that's x over r. So there you go, all of a sudden you have the relationship between the x coordinate and the polar coordinates, r and theta. And then the other trigonometric function, sine of theta, is the opposite side, which is y, over the distance r, so y equals r sine of theta. So this is the relationship between the two. And in practice, you should also know two additional relationships, because these are very useful in many cases when you have to go back and forth between polar coordinates and or Cartesian coordinates. For example, if I square both sides and add the two equations, so x squared equals r cosine theta squared, which is r squared cosine squared theta, and then the same thing for y squared. If I add the two together, because sine squared plus cosine squared is 1, then I get that x squared plus y squared is r squared. And then another very useful relationship is if you divide, provided cosine is not equal to 0, of course, if I divide the two, y over x, I get r sine over r cosine, which is tangent of theta. So that's another useful relationship, y over x equals tangent of theta, provided, of course, cosine of theta is not equal to 0, which happens for, pi over 2, 3 pi over 2, plus minus multiples of pi. So these are useful. So again, these are the first rectangle here. These are the relationships between the Cartesian and the polar coordinates, and these are additional relationships between x, y, r, and theta that are very handy in many situations. And perhaps the easiest and the simplest justification for these additional relationships is when you think about how you represent curves in polar coordinates. I'm going to touch on that in more details later, but think about a full circle. Let's say you have a circle of radius 3 and centered at the origin, right? So let's say you have this picture over here with radius 3. And you know from the Cartesian coordinates that the equation of that circle is x squared plus y squared equals 9. Right? That's the equation of the circle centered at the origin of radius 3. If you decide to write it in polar coordinates, the same picture, the same curve, well, you're going to plug in r cosine, r sine, but you're going to end up essentially with x squared plus y squared equals r squared. So in other words, when you move from Cartesian to polar coordinates, it's very useful to remember that x squared plus y squared is r squared, because that may simplify the computation quite a lot. In the case of a circle, that is it in terms of the equation, right? So if I plug in r cosine, r sine for x and y in the equation of that circle, this is going to be equivalent to r squared equals 9. R is greater than 0, and that means r is equal to 3. So again, remember I mentioned in the previous lecture, that's one of the best, or probably the best example of why it's so nice to have polar coordinates, because the equation of the circle could be much easier to represent. You also have to say what theta belongs to, because for example, if I want a full circle and nothing more, then that means theta belongs between 0 and 2 pi. So the full circle. So compare, if you want, in terms of how easy it is to represent, how it looks like in Cartesian coordinate, how the circle looks like as a function of x. So if I get y by itself, I get this equation for the equation of a circle, 2 branches, plus minus square root of 9 minus x squared. With the Cartesian coordinates representation, which is r equals 3 with theta between 0 and 2 pi. So in general, as a curve in polar coordinates, you essentially get r in terms of theta. But you can imagine that there are many applications when this representation in terms of polar coordinates is much easier to deal with. Okay, so for now, let's actually practice with some examples of moving from polar coordinates to Cartesian coordinates. So write these points in Cartesian coordinates. So they are given in polar coordinates, and you want to write them in Cartesian coordinates. So let's say the point is 4 pi over 3. Well, moving on to Cartesian coordinates is pretty straightforward. all you got to do is to plug in r cosine theta, r sine for x and y. So 4 cosine of 4 pi over 3. You may use the calculator if you want. 4 pi over 3, it's going to be like, what is it? Because like 60 degrees minus 1/2, right? So 4 times minus 1/2. So that's going to be minus 2. And y, r sine of theta, which is 4 sine of 4 pi over 3. And that's also negative, minus root 3 over 2, which is going to be minus 2 root 3. So the same point in Cartesian coordinates will be minus 2 root 3. So let's do 2 more before we move on to the other page. The point minus 2, 3 pi over 4, again in Cartesian, in polar coordinates. Let's actually do a little sketch here. The one with positive 2 is over here. 3 pi over 4 in positive way, 2, and then minus 2 will be the symmetric one. So the point in question will be here. And in Cartesian coordinates, it's going to be minus 2 cosine of 3 pi over 4. Cosine of 3 pi over 4, that's minus root 2 over 2. So that gives me square root of 2. And y minus 2 sine of 3 pi over 4, which is minus 2 times root 2 over 2. And that simplifies to minus root 2. So this point in Cartesian coordinates is root 2 minus root 2. Just as an exercise, why don't you pause the video and figure out the Cartesian coordinates of minus 3 minus pi over 3. And your answer should be minus 3 over 2, 3 square root of 3 over 2, if you did the computation correctly. So let's see how we go from Cartesian to polar coordinates for each point. Couple of examples, and I think we're gonna finish with some basic sketches and how we represent in general a curve in polar coordinates. So stay tuned. All right, so from Cartesian to polar coordinates, here we're gonna make use of those additional relationship between the polar coordinates and Cartesian coordinates with the tangent and x squared plus y squared equals r squared. So you are given the Cartesian coordinates. So let's say as an example that I have the point of coordinates root 3 and 1. So these are the Cartesian coordinates, and I want the polar coordinates. And also you're gonna actually use inverse tangent when you find theta. Remember that when you apply inverse tangent of anything, then the range that the calculator gives you for the inverse tangent is going to be that angle between minus pi over 2 and pi over 2. That's important to remember because the quadrant will be different, could be different for your point. So you have to adjust the angle in that case. So remember, whatever the calculator gives you, it gives you the answer between minus pi over 2 and pi over 2 when we apply inverse tangent. So in this case, the point is in the first quadrant, right? So let's say this is root 3 and this is 1. And I need to find r and theta. So r is the easiest thing to, it's easy to find. We just plug in x and y into that relationship. So that means r squared equals 3 plus 1, which is 4. If you want a positive r, that means r is equal to 2. So that's the first coordinate. Now for the angle, tangent of the angle that you need to find is y over x, which is 1 over root 3. And now with the calculator, if necessary, in this case you might recognize the angle, apply an inverse tangent, and that's going to be in this case pi over 3. Pi over 6, 30 degrees. So that's what it is, right? The answer is in the first quadrant where your point is located. So the point in polar coordinates is 2 pi over 6. right, corresponding to the point root 3, 1 in Cartesian coordinates. But again, like I said, you have to pay attention to the quadrant. So let's say, as another example, let's say the point in question is minus root 3 and 1. So that's going to be in the second quadrant, right? So x minus 3, and this is 1. And we need to measure this angle over here. Now, the radius happens to be the same in this case. So the value of r, x squared plus y squared equals r squared minus root 3 squared plus 1 squared, again, is 4. So that gives you r equals 2. That's the same thing. But when you take the tangent of theta, which is again y over x, and use the calculator to compute theta, the calculator will give you minus pi over 6. So the calculator will give you, actually, look carefully on the picture, it gives you this answer. And obviously you're going to need this. This is your actual theta. So your actual theta is going to be, well, from minus pi over 6, you need to add pi to reach that point. So minus pi over 6 plus pi, which is going to be 5 pi over 6. Right? Because it's going to be on the same line but opposite to it. So therefore this point will be in polar coordinates given by 2, 5 pi over 6. All right. Of course, if you want, for example, let's say if I want negative r, if you so desire to have it as a negative r, then that negative minus 2 should be the opposite of the point of coordinates 2 minus pi over 6. So the point in question, let's call it P. P is the opposite of the point 2 minus pi over 6. So therefore you could view this P as minus 2 minus pi over 6. This is just for practice, right? So minus 2 minus pi over 6 is another way of another set of polar coordinates, but with a negative r. Okay, so with that in mind, let's move on with a couple of figures, geometric figures that can be represented in polar coordinates. So let's see how we can sketch some basic figures with polar coordinates. All right, so how do we represent curves or more general regions in polar coordinates? Well, first of all, a function or a curve in polar coordinates typically is represented by r as an equation in theta. There are variations of this, of course, but typically by default, just like in Cartesian coordinates, you have y as a function of the other coordinate, or you could have x as a function of the other coordinate, right? So you have basically two default versions in Cartesian coordinates, y, one of them as a function of the other one. Here, typically, you specify r as a function of theta. So in that sense, so that's basically the general way of representing a curve. So in that sense, the circle, so of course you have a function of theta with a certain domain. So typically you have r equals f of theta with some domain for theta, or you could have basically an infinite domain for theta, although that's usually not that often encountered because, depending on the situation, that could mean, for example, traversing a curve infinitely many times, but typically you have an interval for theta. So in that sense, you could view actually a circle as a constant function in theta. What I mean is that a circle, to be more precise, centered at the origin. If it's not centered at the origin, that's a little bit different. I'll get into that maybe at a different point in another lecture. But the circle of radius 3, the circle of radius 3 that I mentioned before is essentially basically a constant function with respect to theta, with theta between 0 and 2 pi. So that's one of the easiest, obviously, curves in polar coordinates. In terms of other curves, like I said, if it's more general, if you have indeed r depending on theta, could be a little bit hard to actually sketch, but here's a non-trivial one, but not that difficult. So let's say I have r equals theta. Again, r as a function of theta. Again, make sure you don't confuse this with Cartesian coordinates, right? I mean, if I told you, let's make this remark in this corner. If I say, okay, what's y equals x as a curve, that's going to be the line, right? The line that goes, to the origin, symmetric with respect to y and x. But here, remember, r denotes the radius, the distance from the point to the origin, and theta is the angle. And here it's easier actually to show you how the picture looks like and then to justify it. This is actually basically like a spiral. If you were to sketch it, it's going to look like this, and so on. So why would it look like that? Well, if I were to actually plot just a couple of points, right? So let's say theta is greater than 0. I forgot to specify here, right? So theta is greater than 0, starting from 0. So let's say you plot theta in r and you just want to plot a couple of points like that, right? So you start with 0 and r is 0, and as theta increases, so let's say you have a point pi over 3, then the radius is the same, pi over 3. So in this case, the curve simply says the radius is equal to theta. And let's say you are at pi over 2, the radius is the same, I mean the distance from the point to the origin, pi, 2 pi, and so on. So if you imagine here, like when the angle is 0, the distance is 0. So you start from the origin, that's part of the curve. And as you rotate this axis, the value of r keeps on increasing, because as theta increases, r increases. So as you rotate, imagine you make this rotation, as you rotate the point, you keep on increasing r, right? So for example, when r is equal to pi over 2, or the angle is pi over 2, which is over here, then the distance is pi over 2. As the angle keeps increasing, r keeps on increasing with each point on the rotation, and so on. So it's going to be an infinite spiral, right? So the more you rotate around the origin, the farther you are from the point itself, from the origin. So that'll be an example where it's kind of easy to see the shape by hand, but in general, it's not easy to sketch. So before we move on to a different page, just put another example here. Let's say, I mentioned already a circle. What if I say that basically not a curve, but I describe a region described by r greater than 0, greater than or equal to 0, and the angle theta restricted between minus pi over 3 and pi over 3. This is not a curve, but a region, because let's see what goes on here, and let's illustrate this by trying to sketch this together. So here the only restriction, one of the restrictions is that theta is between minus pi over 3 and pi over 3. The bounds for theta are always sides of angles, right? Remember that theta is an angle with the polar axis. So minus pi over 3, let's say, is this. That's going to be the lower bound. And pi over 3 is going to be the upper bound here. So this is minus pi over 3. This is pi over 3. And then theta varies in between these. And because the radius r can be any number positive, that fills in the entire region inside this angle. It's kind of messy here, but basically the region is going to be the interior of this angle, right, between minus pi over 3 and pi over 3. So let's move on with a couple of other examples before we call it a day. Might be useful to pause the video and see if you can sketch this. So in this example, we have bounds for both theta and r. Now remember, if I have just r equals 1, that's a full circle of radius 1. R equals 9 is a full circle of radius 9. So basically, to say that r is between 1 and 9, that's like being in between two circles. So that's the meaning of bounds for r, constant bounds. And this is between two sides of an angle, just like before. So I hope you visualize, in this case, what goes on. And let's see how it looks like. You can start by sketching with a dotted line, because it's not going to be the full circle. Imagine you have the two concentric circles between 1 and 9, radius 1 and radius 9. And then identify the bounds for theta. So pi over 3 is over here, let's say. 2 pi over 3 is going to be over here. So that's going to be 2 pi over 3. So between the circles of radius 1 and 9, and in between these two angles. And that gives me this piece of the region here. I hope you appreciate how useful this representation is. In Cartesian coordinates, this is actually kind of a small nightmare. I mean, depending on what you have to do, especially the conditions, I mean, for x and y, I mean, depending on the problem, you have square roots, 1 minus x squared, 1 minus y squared. It could be pretty tedious, whereas in polar coordinates, the whole region is just described by two ranges of two variables, one for r and one for theta. Now, if you, for example, want to go from a curve in Cartesian coordinates to a curve in polar coordinates, let's say I have, well, let's just do another quick example. I think that's it for today. So, for example, how would a line look like? So how does a line look like in polar coordinates? Because obviously in some cases, actually different figures may look worse in polar coordinates. So it depends on the situation. But technically or theoretically, there's no limitation on which curve can be written in terms of polar coordinates. Let's say I want to express or to sketch the line x equals 5, which is a vertical line, in polar coordinates. Well, remember the relationship between polar and Cartesian coordinates. So x equals 5 in polar coordinates is equivalent to stating that r cosine of theta equals 5. Here things can be a little bit more tedious or a little bit more subtle, because, you know, how would you write this as a function of theta, right? I have to write r as 5 over cosine of theta. And you may wonder, well, what happens if cosine of theta is equal to 0? Can it be equal to 0? And it cannot be, but what happens if it's close to 0? Well, if you look at how the polar angle looks like, if I look at different points on the line, you notice that actually theta varies between minus pi over 2 and pi over 2, but not equal at the endpoints. Because as theta approaches, for example, minus pi over 2, the line gets nearly vertical, right? Because it's, you know, imagine this line goes further down, infinitely down basically, right? It's an infinite line up and down. So as theta approaches that pi over 2, that point on the line, or r if you want, approaches the point at infinity, right? I mean the distance from P, from the point P and the origin, so the distance from P to the origin O basically goes to infinity as theta approaches pi over 2 and minus pi over 2. So this is a valid representation, but one has to be careful, of course, to specify the domain carefully, right? Because obviously it's not defined that pi over 2 or cosine is equal to 0. But in most of the applications, like I said, we have curves which kind of make sense in polar coordinates, like circles, ellipses, things like that that are more suitable for this representation. So that's it for today.